So today we are going to start lecture 57 of our optimization series, and today's lecture is about creation of the mating pool. And again, I'm Dr. Ranjan Ganguly. So today we are going to talk about how you create the binary strings and then select some of these binary strings for further work as far as creation of the mating pool is concerned. So now we presume that you have the binary strings for all the design variables. So once you have that, you need to calculate the function value, and typically the function value is expressed in terms of the real design variables, where I mean the real number values of the design variable. So what you need to do is that you need to take every binary string, you need to figure out what is the decoded value, and then you need to figure out what is the real coordinate corresponding to this decoded value. For example, in our previous example, if we start with a two variable string such as this, where we have coded each variable using 4 bits, that leads to the decoded value 7, 1, and this in turn leads to the real coordinates 4.67 and 0.67. And if we then plug in these real coordinates into the fitness function, then we get the value of the function f at this particular point given by this binary string. So that's very important to remember that GA is working with binary strings, and corresponding to each binary string there is a real number design vector. So now that we have created the population at these capital N points, we essentially can calculate the function values at each of these N points, and these are represented by F1, F2, F3 all the way to F of N. So these are the function values of the entire population. So this is something we need to do at each generation of the GA. Now once we have done that, we can calculate the mean fitness at generation K, which is essentially given by this F bar K, that is F1 plus F2 all the way to Fn divided by N. That's the simple mean. Now in general, if the GA is well formulated, this mean fitness F bar will keep on growing up as the generations progress, so as K increases. Now in each generation you need to figure out what is the best design point, so that we call as X superscript max K. That's the best value, and this best value corresponds to the value at which the fitness function is a maximum. So the F max value would be the maximum value among all those N points you have calculated, and then corresponding to this maximum function you find out what is the exact design variable. So these values need to be saved at each K. So at each K you essentially track the maximum function value and you track the best design point, because at any point you take the best design point and declare it to be the optimal design. So that would be the best design point obtained until now, or in all the generations which you have traversed until now. So essentially this process which we are going to discuss today is known as reproduction, and reproduction selects good strings from a population to form a mating pool. So this is the first thing which we do on the population, and essentially just like in natural societies, what happens is that the better strings are picked from the current population and they are earmarked for reproduction. So what happens is that multiple copies of these better strings are inserted in the mating pool, and this is accomplished in a probabilistic manner, which we are going to discuss next. Now, two popular approaches are there for creating the mating pool. One is the roulette wheel selection, and the second is the tournament selection. So we are going to discuss roulette wheel selection next. So basically here what happens is that the string I in the population is selected with a probability proportional to its fitness value. And we assume that population size is kept fixed in a simple GA. The sum of probabilities of each string being selected for the mating pool must be 1. Therefore, the probability of selecting string number I in the mating pool would be the function value I, Fi, divided by the total sigma j is 1 to n Fj. So essentially, this is the summation of the function values at the entire population point. And Fi is the function value at the current point I. So this is the probability here. And n, of course, as we know, is the population size. Now this will become very clear if we look at an example, which we will do soon. So the main concept to remember is that this roulette wheel mechanism makes copies of string I in the mating pool, and the selection is based on first creating a cumulative probability of each string being copied. So let's now look at our simple example. So I have created this example with 5 strings, 1, 2, 3, 4, 5. And essentially for each of these strings, we have a fitness value which has come from some function. So now we calculate this probability for each of these fitness values. So this is done using the formula we discussed before. So for example, first thing we do is we take the summation of all these. So that sigma j is 1 to n Fj, and that comes out to be 119. That's the sum of these 5 numbers. So now say you want to get the first value, you take 25 and you divide it by 119. That gives you 0.21. You take 15 and you divide by 119. That gives you 0.126 and so on. So that's the probability corresponding to each string. The next thing is you find the cumulative probability. And this is essentially the probability up to the string or up to the point which has happened till now. So in the first case, it's simply 0.21. In the second case, you take 0.21 and you add 0.126 to it, so you get 0.336. Then you take 0.336, you add the current point to it, you get 0.7225. Continue similarly. The last point you take 0.8315, add 0.168 to it, and you get 1. So at the end of this summation, your probability should become 1. Your cumulative probability should become 1. So that is something which will happen in simple GA. So this process is now quite simple to see, and we are going to now use these cumulative probabilities to actually place the string in the appropriate location. So in some examples, the numbers are going to fall here in this range 0.336 and 0.7225, and so we may pick this string and so on. So string I in the population has a cumulative probability between pi minus 1 and pi. The first string represents the cumulative probability between 0 and p1, and the cumulative probability of a string will lie between 0 and 1. And the cumulative probability of string n must be 1. And all these factors are visible from the simple example we saw in our previous slide. So you can always go back and check it out. Now to form the mating pool, we create n random numbers between 0 and 1. And then we select string j corresponding to the cumulative probability range within which the random number lies. So again, this will become very clear using an example. So let us say we create a random number and this comes out to be 0.5687. Now if we look at this and the cumulative probabilities in the table mentioned previously, this number lies between 0.336 and 0.7225. So this range corresponds to string 3. So what we do is we pick string 3 and add it to the mating pool. Now what we are going to do is a numerical experiment in the next slide, and I'm going to create 5 random numbers and select the strings corresponding to those. So here is my 5 random number set. So we already discussed one of the numbers here, but let's say this number is there. Now this falls in the cumulative probability range point between 0 and 0.21. So we select string number 1 for the mating pool, which is within this range. Now this number we saw lies in this probability range, 0.336 and 0.7225. This corresponds to string number 3. So this string corresponds to fitness value of 46. This number here, this falls in cumulative probability range between 0.21 and 0.336, corresponds to string 2, fitness value 15. And similarly, two more random numbers are here, and these fall inside these two probability points. So again, these correspond to 1 and 3. So you are seeing the logic here is that the greater probability of falling in a larger band is there. So that's how the strings get selected depending on the fitness value. And remember that these probabilities are directly proportional to the fitness value. So what happens here is that now we ended up creating multiple copies of some strings, for example, 1 and 3 here. And these strings tend to have a higher fitness value. So our fitness, which is the total or mean fitness of the population, has gone up. So this is something which will typically happen because you are selecting the values for which the fitness is more. And this is very typical to what happens in a normal mating pool, where the specimen who are more fit are typically selected. So we see that the roulette wheel selection selects more copies of the fitter string 1 and 3. Strings 4 and 5 end up being discarded. So the fitness of the population in the sense of the mean has gone up. So now we select the mates by taking the strings corresponding to, for example, 1 and 3 and 2 and 1. And let us say we don't generate the fifth point, we just take the best point and continue with that as the fifth point. So we are crossing something like 0.8 of the population. So now this strategy of keeping the best string without any change is something which is sometimes done in GA, and it can lead to better results in many cases. So this is known as elitism. And we can see that one of the negative consequences could be that it could lead to a loss of diversity in the population. But a positive consequence could be that you have kept aside the better genetic material here. So now the typical roulette wheel selection we have discussed until now has two problems. The first problem takes place if the population contains a string which is exceptionally fit. In this case, what will happen is that there will be too many copies of this exceptionally fit string in the mating pool, and therefore the diversity of the mating pool is going to be reduced and the GA may stagnate in such a scenario. So that's the first limitation of the roulette wheel selection the way we have defined it. The second problem could happen when you have several strings which are equally good. And in this case, once again, this particular good string would get copied into the mating pool too many times, and there would be hardly any change in the population after a certain point. That is stagnation here also. So both these problems can be mitigated to some extent by using a certain linear transformation, where you essentially define a scaled fitness function S in terms of the actual fitness function f, and you pick a and b as two constants which are defined such that the best string in the population is given a predefined number of copies in the mating pool and give a typical mean string 1 copy in the mating pool, and this should be performed at each generation k. So this was roulette wheel selection. Now beside that, several other methods have come up for selection of the mating pool. We are going to discuss tournament selection as a method, which is again quite popular. So in tournament selection, a subset of points is randomly picked from the population, and the best string from this subset is selected for the mating pool. typically binary tournament selection is popular. And if you compare this with nature, this binary tournament selection does model mating competition in nature, where you will typically see a kind of competition between two specimens of a certain species to mate. So that's something we are trying to model here. So to start this process, the first thing you need to do, which you should do in general, is that the entire population should be shuffled randomly so that there is no listing or sequential growth in any of the members or the population. Then you select the first S strings, 1, 2, 3, S minus 1, S. You pick from the top of the deck and then choose the best in this particular pack. So think of this like a game of cards. So the best string would be selected for the mating pool. Now in binary tournament selection, you would just take the first two strings. So you would have 1 and 2. That is, S would be 2. So that's the simplest model, where you essentially have a competition between two people. It is like a duel or like a binary game. Now in the next step, what you would do is you would select the next S string and then find the best string for this particular mating pool. This process is continued till all members of the population are selected for mating. Now the whole population is once again shuffled. The process is repeated until the mating pool is formed, and we will look at how this tournament selection works by considering the simple problem we created before with only 5 points, and we'll do 2 shuffles to create a mating pool. So let's start with this example for tournament selection. Let's say we have 5 strings here. Corresponding to these strings, there are 5 values of fitness here. Now let's create a tournament between the first two strings here. So between 25 and 15, better one is 25, so this survives. String 1 survives. 15 is decimated. 46 and 13, 46 survives. 13 is decimated. So based on these two tournaments, we get 1 and 3 as one pair, which is selected for reproduction. Then we shuffle the strings. Once we have shuffled it, we create one more tournament. We take these two, create a tournament. 15 survives because it is greater. That's string 2. One more tournament here. 25 survives. That's string 1. So we then pick these two strings, 1 and 2, and create the second mate pair. And so we can use these two mate pairs in conjunction with probably the best value. We could add a string 3 there, and then that would be our mating pool. So you see that tournament selection is actually in some ways a very simple process. It's more binary, more in terms of a game, and to some extent it does mimic a natural selection scenario. But a natural selection scenario is also captured to some extent by the roulette wheel selection. That is probably for more complex species which would use such a mechanism. So we can say in summary that modified roulette wheel selection using linear transformation of the fitness function is a good approach for selecting a mating pool. Second approach would be tournament selection. So let us see what exactly is happening in this selection of the mating pool. You can see that good strings in the population are getting assigned a larger number of copies for the creation of the mating pool. That's what's happening. But bad strings are being decimated from the population. This is very Darwinian, but this is exactly what is going on here. And you will observe this if you watch any species, if you watch National Geographic channels and so on. They'll always be talking about the herds and how there is mating competition, how also sometimes some of the contenders do die in the process. So that is something which is being mimicked here, something like a squid game. So one of the things we observe is that no new strings are created during the creation of the mating pool. No new points in the design space are explored. So that is something which is very interesting. All that has happened is that we have taken better strings and we have created a mating pool. So how do we create new points or new strings? Well, that's going to be next lecture and we are going to cross the genetic material between the two strings here which have been selected for mating. So that is essentially the model of reproduction, where essentially you have a male and a female in terms of the chromosomes, and then they exchange genetic information, and then an offspring is born. And typically it is hoped that if the mating pool is well selected, the offspring is likely to be better. Well, of course, if it is not better, it is once again subjected to the vagaries of the Darwinian natural selection process, and again it may get decimated in the next round. So as far as this method is concerned, it is very robust. It's very difficult to survive in a GA unless the string is very good. So today we covered two important topics: roulette field selection and tournament selection. And so now we know how to create a mating pool. There are some more advanced methods of selecting the mating pool. We may discuss that later, such as multi-point tournament selection and so on. So you could have a tournament selection where S may not be 2, S may be larger. So I will stop this video here. I will see you in my next video.